In this video, we'll explore the reactions and versatility of alkynes in organic chemistry. We'll begin with a review of the fundamental properties of alkynes, followed by a discussion on how the pi electrons in alkynes function as nucleophiles in various reactions similar to alkenes. Then we'll dive into a detailed exploration of key alkyne reactions, covering their key reactive partners, mechanisms, reagents, and synthetic products. Let's begin the video with a review of alkynes. Alkynes are hydrocarbons characterized by at least one carbon-carbon triple bond consisting of one sigma bond, sp orbital overlap, and two weaker pi bonds, sideways p orbital overlap. These two pi bonds make alkynes more reactive than both alkanes and alkenes. The triple bond has a linear geometry with bond angles of 180 degrees, and this rigidity eliminates the possibility of cis-trans isomerism. Alkynes are less common in nature compared to alkenes, but their unique reactivity makes them valuable intermediates in organic synthesis. Up until now, we haven't discussed any reactions involving alkynes. Let's start by focusing on their synthesis, exploring the methods used to create these highly versatile compounds. Recall that alkenes can react with X2 and dichloromethane to give vicinal dihalides. Alkynes can be synthesized from vicinal or geminal dihalides through double elimination reactions. Recall that elimination reactions, which convert alkyl halides into alkenes, require a strong base and a good leaving group. For instance, treating an alkyl halide with potassium tert butoxide and butanol leads to an E2 elimination, yielding the corresponding alkene product. By a similar process, vinyl halides can undergo E2 eliminations to form alkynes. For example, a vicinal dihalide, where vicinal means on adjacent carbons and di indicates two halides, reacts with one equivalent of a strong base to produce a vinyl halide. This intermediate then undergoes a second E2 elimination with another equivalent of base to give the corresponding alkyne. Sodium amide, NaNH2, in ammonia is commonly used as the base in this reaction due to its strength. In the first step, sodium amide deprotonates a beta hydrogen in an E2 mechanism, resulting in the formation of a vinyl halide intermediate. In the second step, a second equivalent of sodium amide facilitates the elimination of the remaining halide, yielding the alkyne. For terminal alkynes, a third equivalent of sodium amide is consumed to deprotonate the terminal CH bond, generating an alkenyl anion. The terminal CH bond of terminal alkynes is unusually acidic, with a pKa of approximately 25. This relative acidity allows a strong base, such as sodium amide, with a conjugate acid ammonia having a pKa of 41 in ammonia, to deprotonate the terminal alkyne in an acid-base reaction. This step produces a third equivalent of ammonia as a byproduct and the highly nucleophilic alkenyl anion. This anion is then protonated during the aqueous workup step, typically with water, to regenerate the neutral terminal alkyne. This reaction also works on geminal dihalides, where two halogens are bonded to the same carbon to give the same terminal alkyne. Thus, synthesizing a terminal alkyne from a vicinal or geminal dihalide requires three equivalents of sodium amide, two for the double elimination and one for the deprotonation of the terminal alkyne, followed by protonation during the workup step. It's important to note that elimination and substitution reactions typically occur at carbons that are sp3 hybridized. However, this reaction represents a rare exception, as elimination can proceed even on an sp2 hybridized carbon system, such as in the formation of vinyl halides during double elimination. In this example, we used a vicinal dihalide in which the two halogen atoms are bonded to a secondary and a primary carbon, respectively. This arrangement facilitates the formation of a terminal alkyne after undergoing a double elimination reaction followed by a workup step. However, consider the following vicinal dihalide, 2,3-dibromobutane, where both bromine atoms are bonded to secondary carbons. Based on what we've learned, we would expect this starting material to undergo a double elimination reaction, yielding the internal alkyne 2-bute. Surprisingly, when 2,3-dibromobutane is treated with sodium amide in liquid ammonia, the reaction produces the terminal alkyne 1-bute rather than the internal alkyne we might predict. Let's explore the reasoning behind this isomerization by examining the energetics of alkyne isomerization in the presence of sodium amide, NaNH2. In the first step, the double elimination initially produces the internal alkyne as expected. The pKa of the terminal CH bond in internal alkynes is approximately 45, making deprotonation by sodium amide NaNH2 a relatively unfavorable reaction. However, in equilibrium, some deprotonation of the alkyne occurs, yielding an alkynyl anion. This alkynyl anion has a resonance form in which the negative charge is delocalized onto an internal carbon of the alkyne. This resonance-stabilized anion then reacts with ammonia in an acid-base reaction, protonating the internal carbon and forming an allyne intermediate. The pKa of the terminal CH bond of the allyne is lower than that of ammonia, allowing for another acid-base reaction with sodium amide to form a terminal carbanion. This terminal carbanion also has a resonance structure that places the negative charge on an internal carbon. The resonance form with the internal negative charge undergoes another acid-base reaction with ammonia, protonating the internal carbon and forming the terminal alkyne. Finally, the terminal alkyne is deprotonated again by sodium amide and protonated in the workup step upon the addition of water. Therefore, regardless of the nature of the starting vicinal dihalide, treatment with sodium amide in ammonia followed by a workup step with water gives the terminal alkyne product. So, if treatment of vicinal dihalides with sodium amide in ammonia followed by water always gives the terminal alkyne through isomerization, how would we synthesize 2-butane from 2,3-dibromobutane? Treating this vicinal dihalide with the comparatively weaker base potassium tert butoxide in dimethyl sulfoxide, DMSO, typically results in the formation of an internal alkyne. While potassium tert butoxide is often seen as a strong base in E2 eliminations, it is weaker than sodium amide when considering the pKa of their conjugate acids. This difference in base strength explains why sodium amide is required for reactions leading to terminal alkynes, whereas tert butoxide often favors the formation of internal alkynes. The isomerization of the internal alkyne to a terminal alkyne is too energetically unfavorable under these conditions. As a result, the internal alkyne remains as the primary product and is recovered after the reaction. Alkyne isomerization can be exploited to interconvert internal alkynes and terminal alkynes. For example, an internal alkyne can be treated with sodium amide in ammonia, followed by a workup step with water to yield the terminal alkyne. This terminal alkane can then be isomerized back to the starting internal alkyne using potassium tert butoxide in dimethyl sulfoxide. This sequence demonstrates how different bases and reaction conditions can control the equilibrium between terminal and internal alkynes. Before diving into the reactions of alkynes, let's discuss a helpful tip. Due to the linear geometry of alkynes, it's easy to accidentally omit carbons when drawing them in line bond form. To avoid this mistake, it's a good practice to explicitly draw the alkyne carbons when you're first learning these reactions. This ensures accuracy and prevents errors in structure. Now we are ready to discuss our first reactions of alkynes, beginning with the alkylation of acetylides and acetylides as nucleophiles. Earlier in this video, we've discussed that the terminal CH bond of terminal alkynes is unusually acidic, with a pKa of approximately 25, which is considerably low compared to the CH bond strength of other hydrocarbons. Treating terminal alkynes with sodium amide in ammonia results in an acid-base reaction that deprotonates the terminal alkyne. The conjugate base formed is called an acetylide, reflecting the trivial name acetylene for ethyne. The carbon bearing the lone pair of electrons is highly nucleophilic, making it an excellent nucleophile and base for a variety of reactions. This reaction is extremely important since it provides another method for carbon-carbon bond formation beyond Grignard reagents. These acetylides can react with the following electrophiles to give their respective products. In alkylation, acetylides can react with alkyl halides or alkanes with other good leaving groups in an SN2 reaction to form carbon-carbon bonds. This reaction requires the electrophilic alpha carbon of the substrate to be sterically unhindered and works best for methyl and primary alpha carbons, following the rules we discussed for SN2 reactions. Acetylides can also react with carbonyls and epoxides in electrophilic addition, similar to Grignard reagents, to form alcohols. The nucleophilic carbon on the acetylide attacks the electrophilic carbon of the carbonyl or epoxide, forming the carbon-carbon bond and generating an alcohol. The type of alcohol formed follows the same pattern as for Grignard reactions. Reaction with formaldehyde gives a primary alcohol, reaction with an aldehyde gives a secondary alcohol, and reaction with a ketone gives a tertiary alcohol. When reacting with an epoxide, the product is a primary alcohol, with the hydroxyl group located 2 carbons away from the alkyne carbon. Finally, acetylides can act as bases, and reacting them with water or deuterated water yields terminal alkyne products via an acid-base reaction. This occurs because the pKa of the terminal alkyne CH bond, approximately 25, is higher than the pKa of water or deuterated water, around 14, making the proton transfer energetically favorable. This is the same reason why we use water as a mild acidic workup to protonate terminal alkynyl anions in the synthesis of terminal alkynes. The remaining reactions we will cover are reactions we have seen before with alkenes. Just like alkenes, alkynes can be reduced or made more saturated through the addition of H2 across the triple bond. We've seen before that alkenes can be hydrogenated to alkanes through treatment with molecular hydrogen in the presence of a catalyst, such as H2 and PDC. We've also seen stereoselective hydrogenation of alkenes to alkanes using Wilkinson's catalyst like ClRH PPH3s3, which gives predominantly syn hydrogenation. Treatment of an alkyne with H2 and PD-C or an equivalent catalyst will result in full hydrogenation, reducing the alkyne completely to an alkane through the addition of 2 equivalents of molecular hydrogen. However, it is possible to stop the hydrogenation at the alkene stage, a process known as partial hydrogenation using specific reagents. Reduction of alkynes with Lindlar's catalyst gives predominantly cis-alkenes, while reduction of alkynes with sodium metal dissolved in ammonia results in the formation of predominantly trans-alkenes. Alkynes can undergo electrophilic additions of hydrohalic acids, such as HCl and HBr. Reaction of a terminal alkyne with a hydrohalic acid, HX, initially forms a vinyl halide with Markovnikov regiochemistry, and upon further reaction, yields a saturated geminal dihalide with Markovnikov regiochemistry. The first step, involving the addition of the first equivalent of HX, is relatively fast, whereas the addition of the second equivalent of HX to the vinyl halide proceeds much more slowly. The Markovnikov regiochemistry of this reaction is governed by the same principles as alkene additions. The more substituted carbon of the alkyne stabilizes the carbocation character, directing the halide to that specific carbon. The addition of concentrated HX to disubstituted alkynes gives only the trans-alkene product where the hydrogen and halide are added trans to each other. This addition involves 1 molecule of alkyne reacting with 2 molecules of the hydrohalic acid to form the trans-alkene product. We will next discuss the addition of X2 to alkynes. Similar to the addition of HX to terminal alkynes, the addition of X2 to an alkyne to form the vinyl dihalide monoaddition is relatively fast, whereas the second addition of X2 to produce the vicinal tetrahalide is significantly slower. The stereoselectivity of the monoaddition resembles the anti-stereochemistry observed in the addition of X2 to alkenes, suggesting that the reaction proceeds through a halonium ion intermediate. This intermediate directs the anti-addition of the halogen atoms across the triple bond, yielding the transvinyl dihalide as the product of the monoaddition. In this reaction, X can be either chlorine or bromine. The final reactions we will cover for alkynes are oxymercuration and hydroboration. Similar to alkenes, we can add water across the triple bond of an alkyne in hydration reactions. These reactions follow the same regiochemical trends as their alkene counterparts, but the resulting products undergo tautomerization to form ketones or aldehydes, depending on the starting materials. Let's begin by discussing the oxymercuration of alkynes. Recall that oxymercuration followed by demercuration of alkenes yields an alcohol with Markovnikov regiochemistry. In this transformation, an alkene is treated with mercury 2 acetate in water and tetrahydrofuran, THF, during the first step, followed by a reduction using sodium borohydride, NaBH4, and sodium hydroxide, AOH, in the second step. The oxymercuration of alkynes, however, employs slightly different reagents. Instead of mercury 2 acetate, we use catalytic mercury 2 sulfate, HgSO4, in the presence of water and sulfuric acid, H2SO4. This reaction gives a ketone product instead of an alcohol. The carbonyl group adheres to Markovnikov regiochemistry, with the oxygen atom attaching to the more substituted carbon of the alkyne. Let's now take a closer look at the mechanism to understand how this transformation occurs. In the first step of the reaction, a mercurium ion is formed, where the alkyne interacts with mercury, 2-sulfate, to create a three-membered ring intermediate. Water then attacks the more substituted carbon of the three-membered ring, similar to the oxymercuration of alkenes. This nucleophilic attack results in the formation of an oxonium ion, which is subsequently deprotonated by another molecule of water. Through the next couple of steps, the carbon-mercury bond is broken, exchanged with a carbon-hydrogen bond, ultimately yielding an enol intermediate. The term enol refers to a compound containing both alkene and alcohol functional groups, with ene derived from alkene and ol from alcohol. Enols are inherently unstable and undergo a process called keto-enol tautomerization, a specific type of tautomerization where the compound interconverts between its enol, alkene, alcohol, and keto carbonyl forms. Tautomerization is the chemical process in which a compound interconverts between two structural isomers, typically involving the migration of a proton and the reorganization of a double bond. In keto-enol tautomerization, a proton transfers from the hydroxyl group of the enol to one of the carbons of the double bond, while the double bond rearranges to form a carbonyl group. This process yields the more stable ketone product, which adheres to Markovnikov regiochemistry in this reaction. Lastly, let's discuss the hydroboration of alkynes. Recall that hydroboration of alkenes yields an alcohol with anti-Markovnikov regiochemistry. In this transformation, an alkene is treated with BH3 and tetrahydrofuran, THF, in the first step, followed by an oxidation using hydrogen peroxide and sodium hydroxide in the second step. For hydroboration to alkynes, dialkylborane R2BH is used as opposed to BH3 so that B and H can only add once across the alkyne. This addition follows the same syn stereoselectivity as hydroboration of alkenes. Following the oxidation in the second step, the enol product is formed, which once again tautomerizes into the more stable keto product, which in this case is an aldehyde. Let's consider one final detail about the oxymercuration and hydroboration of alkynes. In the examples we discussed, a terminal alkyne underwent these transformations, yielding the Markovnikov and anti-Markovnikov enols, which tautomerized to their respective keto forms, a ketone and an aldehyde. For internal alkynes, however, the outcome is different. Regardless of whether oxymercuration or hydroboration is used, the final product is always a ketone, because the reaction does not favor anti-Markovnikov regiochemistry in internal systems. Consider the symmetrical internal alkyne 2-butyne. The transformation of 2-butyne under either oxymercuration or hydroboration produces the same ketone product, since there is only one possible pathway for tautomerization. On the other hand, for unsymmetrical internal alkynes like 3-heptene, the reaction can produce two distinct ketones, as there are two possible positions for the resulting carbonyl group, depending on which carbon of the triple bond becomes part of the ketone. Ultimately, when reacting a terminal alkyne, oxymercuration gives the ketone product, while hydroboration gives the aldehyde product. However, for internal alkynes, both reactions yield a ketone product with the possibility of forming two distinct ketones if the starting alkyne is unsymmetrical. As always, let's do some practice. Propose reaction sequences to accomplish the following transformation. Specify the necessary reaction conditions and reagents. You may use any building block with less than or equal to 2 carbons for your syntheses. However, the reagents that you use, which are not incorporated into the final product, may contain more than 2 carbon atoms. The structure of the reactant and the product should be shown for each chemical transformation. Feel free to pause the video and try these problems on your own first. In the first reaction, 2-butene is transformed into 2,3-dimethyl-2-butene. To determine the required steps, we can use retrosynthetic analysis, working backward from the product to identify the intermediates and reactions needed to achieve the transformation. First, we observe that the product contains 2 additional carbons compared to the starting material. Additionally, The alkyne in the starting material has been reduced to an alkene. Using these observations, let's work our way back to the starting material. The tetrasubstituted alkene product could have been formed through an E1 elimination reaction, which would give only the tetrasubstituted alkene rather than disubstituted alkenes. We know a reaction that gives exclusively the elimination product via carbocation intermediate with no SN1 competition. The elimination of an alcohol using sulfuric acid and heat. This brings us one step back to a tertiary alcohol. We know that tertiary alcohols can be formed from the reaction of ketones with Grignard reagents, so one step back from this molecule could have been the ketone. This ketone could have been made through the oxidation of a secondary alcohol, bringing us another step back. Now, looking back to the starting material, we can see that there is only one more carbon atom in our current structure than in the starting material. This leads us to believe that the carbon atom was added via a Grignard reaction to an electrophile. The molecule as it stands is not an electrophile that reacts in a Grignard reaction, but we can go one step back to determine which electrophile it could have been. The secondary alcohol could only have been derived from one of two electrophiles, an aldehyde or an epoxide. If it were an aldehyde, the addition of the methyl Grignard reagent would result in a product where the carbon-carbon bond forms at the wrong carbon. Therefore, this molecule could only have been formed from a symmetrical epoxide that was ring-opened using the methyl Grignard reagent. This epoxide could have been either the cis or the trans isomer, but I have drawn only the cis isomer here for simplicity. We don't know any direct methods to make epoxides from alkynes, but we do know how to synthesize them from alkenes. This epoxide could have been derived from the cis alkene, which we know can be made from our starting material, bringing us full circle to the beginning. Note that the trans isomer of the epoxide could also have been used, which would yield the trans alkene and the trans epoxide. Using this retrosynthetic analysis, we can now outline the forward synthesis for this transformation. In the second reaction, acetylene is transformed into the following product. This is a challenging problem, but to determine the required steps, we can use retrosynthetic analysis, working backward from the product to identify the intermediates and reactions needed to achieve the transformation. Looking at the product, we see a cyclopropane ring where each of the hydrogens and alkyl groups are trans to each other. Although we do not know of methods to directly form cyclopropane rings from alkynes, we do know that cyclopropanation reactions can be performed on alkenes. Given that stereochemistry is conserved in cyclopropanation reactions, the trans stereochemistry of the product suggests that it was derived from a transalkene. This transalkene could, in turn, have been formed by the partial hydrogenation of an alkyne. This leads us to the alkyne precursor. Comparing this alkyne precursor to the starting material, acetylene, we notice that each of the hydrogens in acetylene has been replaced, one with a methyl group and the other with a carbon group bearing a secondary alcohol. Let's first determine how the more complex carbon group containing the secondary alcohol could have been introduced. The carbon bearing the hydroxyl group in the secondary alcohol is directly adjacent to the alkane carbon. This suggests that the group was formed by the nucleophilic ring opening of an epoxide, specifically propylene oxide, using an acetylide as the nucleophile. However, due to the two-carbon limitation outlined in the instructions, we cannot simply add a commercially available three-carbon epoxide like propylene oxide to our acetylide nucleophile. Instead, we must synthesize the epoxide starting from acetylene. Here's how we can construct the desired epoxide. React acetylene with sodium amide, NaNH2, in ammonia to deprotonate it, followed by treatment with methyl iodide in dimethyl sulfoxide, DMSO, to form propyne. Subject propyne to partial hydrogenation using molecular hydrogen H2 in a catalyst, such as Lindlar's catalyst, to produce the cis-alkene. Partial hydrogenation using sodium metal in liquid ammonia to give the transalkene is also possible, as the stereochemistry of this alkene does not matter in the long run. Treat the cis-alkene with a paracid, such as metachloroperoxybenzoic acid, MCPBA, to perform epoxidation, yielding propylene oxide. Now that we've synthesized propylene oxide, let's return to the acetylide nucleophile. Another molecule of propyne can be treated with sodium amide in ammonia to form the acetylide. This acetylide can then attack the less substituted carbon of the epoxide in a nucleophilic ring opening reaction. This reaction produces a carbon group attached to a secondary alcohol. Finally, an acid workup protonates the oxygen, completing the formation of this group. At this stage, we've constructed the alkyne precursor with both the methyl and the secondary alcohol containing carbon group. From here, partial hydrogenation of this alkyne using sodium metal and ammonia produces the transalkene. The transalkene undergoes cyclopropanation to yield the desired cyclopropane product, with the trans stereochemistry conserved. That was a lot, so here is the forward synthesis for this transformation. This marks the end of our Organic Chemistry 1 course series. As always, thank you for watching. I hope you found it helpful, and best of luck in Organic Chemistry 2.